Genetic algorithms versus traditional methods. The battle between genetic algorithms and traditional optimization methods is not merely academic, it's shaping the future of problem-solving in artificial intelligence, engineering design, finance, and countless other domains. While conventional techniques like gradient descent or linear programming offer precision and speed in well-defined scenarios, they often falter when faced with complex, dynamic environments where solutions are not easily quantifiable. Genetic algorithms, GAs, inspired by natural selection and evolutionary biology, provide an alternative approach that thrives in ambiguity. Unlike deterministic methods, GAs explore vast solution spaces through stochastic processes, mimicking biological evolution's ability to adapt over generations. This makes them particularly useful for problems with nonlinear constraints, high dimensionality, or unknown optimal points, areas where traditional approaches may struggle or fail entirely. The evolutionary foundation of genetic algorithms. At their core, genetic algorithms draw inspiration from Charles Darwin's theory of natural selection, applying principles such as mutation, crossover, and selection to evolve better solutions iteratively. These mechanisms allow populations of candidate solutions to evolve toward increasingly effective configurations without requiring explicit knowledge of the underlying mathematical relationships. This bio-inspired methodology enables GA to tackle problems that lack clear gradients or differentiable functions, a limitation inherent in many traditional numerical optimization techniques. By using probabilistic operators rather than strict rules, GAs can navigate rugged fitness landscapes that would confuse local search algorithms like hill climbing. Evolutionary principles, mutation, introduces random changes in individual solutions to maintain diversity within the population and avoid premature convergence. Crossover combines features from two parent solutions to generate new offspring, potentially combining advantageous traits from both parents. Selection determines which individuals get to reproduce based on their performance, fitness, in solving the given problem. The interplay between these three fundamental operations creates a self-regulating system capable of exploring diverse regions of the solution space while gradually refining promising candidates. This process mirrors how species adapt to environmental pressures across generations, making GA a powerful tool for adaptive computing. Diverse applications across industries, from scheduling airline crews to optimizing stock portfolios, genetic algorithms have found practical applications across numerous industries. Their versatility stems from their ability to handle multi-objective optimization problems where trade-offs between competing goals need careful balancing. In manufacturing, for example, engineers use GAs to optimize production line layouts, minimizing costs while maximizing throughput efficiency. Similarly, in logistics, route planning systems leverage GA to find near-optimal delivery paths considering real-time traffic conditions and fuel consumption rates. A notable application comes from the field of robotics, where researchers employ genetic algorithms to evolve control strategies for autonomous vehicles operating under uncertain terrain conditions. By simulating thousands of potential movement patterns and selecting those yielding best results, robots can learn to traverse complex environments effectively. Beyond technical fields, even creative disciplines benefit from GA-based tools. Artists and designers utilize evolutionary computation to generate novel visual designs, music compositions, or architectural forms by defining evaluation criteria that guide iterative refinement towards aesthetically pleasing outcomes. Evaluating fitness functions effectively. Fitness function definition plays a critical role in determining GA success. It acts as the primary metric guiding selection pressure during each generation cycle. An improperly defined fitness landscape might lead to suboptimal convergence or prevent discovery of truly superior solutions. Designing an appropriate fitness function requires deep understanding of domain-specific requirements alongside computational feasibility considerations. For instance, in drug discovery research, scientists define custom metrics evaluating molecular properties against desired therapeutic effects while also accounting for pharmacokinetics profiles. Some advanced implementations incorporate penalty terms within their objective functions to discourage undesirable behaviors automatically. This technique helps steer searches away from invalid states without needing explicit constraint enforcement mechanisms. To ensure robustness, practitioners often implement multiple parallel evaluations tracking various aspects simultaneously. This allows identification of Pareto frontiers representing sets of non-dominated solutions satisfying distinct combinations of objectives efficiently. Challenges in implementing genetic algorithms despite their power. Implementing successful genetic algorithms presents several challenges ranging from parameter tuning difficulties to issues related to premature convergence and scalability limitations. One common pitfall involves setting improper values for key parameters such as population size, mutation rate, and crossover probability. Too small populations risk losing valuable genetic material before sufficient exploration occurs. Too large ones consume excessive computational resources unnecessarily. Similarly, choosing inappropriate representation schemes can severely impact effectiveness. Binary strings work well for certain types of problems but become inefficient when dealing with continuous variables requiring fine-grained adjustments. Moreover, handling deceptive landscapes remains challenging since local optima can mislead evolutionary progress significantly. Techniques like niching or crowding help mitigate this issue by maintaining diversity among coexisting solutions. Scalability poses another concern, especially when applied to very large datasets or highly dimensional feature spaces. Efficiently managing memory usage becomes crucial here due to exponential growth potential associated with increasing complexity levels. Optimizing performance through parameter tuning parameters correctly represents one of most critical steps in achieving good GA performance. Parameters include population size, elitism strategy, operator probabilities, and termination criteria, all influencing overall behavior dramatically. Population sizing affects both exploration capabilities and resource utilization needs. Smaller groups reduce processing overheads at expense of reduced diversity, whereas larger samples increase chances discovering global optimum, albeit consuming greater CPU cycles. Varying mutation rates introduces controlled randomness necessary for escaping plateaus encountered frequently in high-dimensional spaces. Careful calibration ensures enough variation exists without compromising stability achieved via accumulated improvements. Selecting suitable termination conditions depends heavily upon specific use cases. Some problems require fixed iteration counts while others monitor improvement thresholds, dynamically adjusting stopping points accordingly. Hybridization techniques combine GA with other metaheuristics, enhance adaptability, further allowing simultaneous exploitation and exploration phases beneficial for tackling difficult combinatorial puzzles efficiently. Comparative analysis with other metaheuristic approaches. While genetic algorithms share similarities with other nature-inspired optimization techniques like simulated annealing or particle swarm optimization, differences exist regarding implementation structure and applicability ranges. Simulated annealing operates sequentially, focusing single solution trajectory guided by temperature schedules controlling acceptance likelihoods during uphill moves. Contrastingly, GA maintains entire population evolving collectively, pursuing better collective outcome distributions. Particle swarm optimization employs velocity vectors updating positions according to personal best experiences plus neighborhood influences, creating swarming dynamics similar yet distinct compared to GA's sexual reproduction model. Each method exhibits strengths, weaknesses depending context. SA excels at avoiding entrapment local minima thanks gradual cooling phase, reducing transition energy barriers progressively. However, lacks intrinsic mechanism promoting diversification beyond initial seeds unless augmented externally. GAs inherently support multi-objective optimization, naturally supporting Pareto frontier analyses directly, unlike PSO, which typically requires additional layers post-processing extraction. Meaningful trade-off curves. Case study: traveling salesman problem using GA. Consider classic TSP problem involving finding shortest possible route, visiting cities exactly once, returning original starting point. Applying GA offers efficient approximate solution, especially when exact answers computationally prohibitive. Representation usually adopts permutation encoding mapping city indices onto chromosome elements, ensuring valid tours generated through crossovers, preserving connectivity integrity essential correct path formation. Initial populations randomly initialized containing feasible routes serving base for subsequent evolutions. Evaluation performed calculating total distance traversed acting primary fitness measure guiding selections. Crossover implemented carefully avoiding duplicates reusing same node twice violating tour constraints. Mutation applies swap operations exchanging pairs nodes maintaining permutation validity crucial correctness preservation. Elitist strategies retain top-performing individuals preventing loss valuable information while introducing fresh variations maintaining healthy balance exploration exploitation duality central GA efficacy. Future trends and emerging research areas ongoing developments continue pushing boundaries expanding GA utility beyond traditional confines opening exciting possibilities emerging technologies integration. Quantum computing promises revolutionary advances enabling faster processing speeds fundamentally altering how evolutionary computations executed. Quantum bit superposition property allows simultaneous evaluation multiple states exponentially accelerating search procedures previously limited classical architectures. Neuroevolution merges neural networks training with GA frameworks, automating architecture design learning processes, eliminating manual feature engineering burdens present conventional machine learning pipelines. Multi-agent systems incorporating decentralized decision-making structures represent another promising direction leveraging distributed GA instances collaborating solve complex coordination tasks arising networked environments. These innovations highlight growing importance GA methodologies adapting evolving technological landscape emphasizing flexibility resilience required modern problem-solving paradigms demanding ever-increasing sophistication. Practical implementation tips for beginners newcomers embarking GA journey should start simple experimenting basic toy problems building foundational understanding before tackling intricate real-world applications. Implementing minimal working examples provides hands-on experience grasping core mechanics without overwhelming complexity. Classic problems like knapsack optimization or binary string maximization serve excellent introductory exercises illustrating basic concepts clearly. Using visualization tools aids comprehension watching generations evolve observing convergence trends identifying potential issues early stages development lifecycle. Engaging online communities facilitates access shared codebases templates offering ready-to-use frameworks saving time effort otherwise spent reinventing wheels. Gradually increment difficulty level progressing toward realistic scenarios mastering. Debugging skills diagnosing failures interpreting outputs critically developing intuition behind effective configurations. Conclusion genetic algorithms stand out as versatile adaptive tools capable addressing wide array challenges confronting contemporary society spanning scientific engineering artistic pursuits alike. By embracing principles derived biological evolution, these algorithms demonstrate remarkable capacity navigating complicated terrains providing viable alternatives constrained deterministic approaches struggling cope uncertainties complexities real-world situations.